In part 1, we covered RAG, retrieving relevant documents at query time and injecting them into the LLM's context. It's the right starting point for 80% of enterprise use cases. But there are situations where RAG hits a wall. Your model keeps using generic language when your domain requires specialized terminology. It structures its outputs inconsistently, even with detailed prompts. It can't reason about your domain the way a human expert would, because the patterns of your domain aren't in its weights. This is when you cross the line from retrieval into training. You modify the model itself. Today, we are going deep on the entire spectrum, from parameter-efficient fine-tuning with LoRA to full weight updates to continued pre-training on billions of tokens. We'll cover exactly when each approach pays off, what it costs, what it demands in data and infrastructure, and how to build it on AWS. Let me set the mental model. There's a spectrum of how deeply you can modify a model's behavior, and it maps directly to cost, data requirements, and impact. On the far left, lightest touch, you have prompt tuning, soft prompts. You're not changing the model at all. You're learning a small set of virtual tokens that steer its behavior. Needs maybe 100 examples. Minimal compute, minimal impact. Move right, LoRA and QLoRA. You freeze the original model and train small adapter matrices, typically less than 1% of the model's parameters. This is the enterprise sweet spot for most fine-tuning. A few thousand examples, 1 or 2 GPUs, meaningful behavioral changes. Continue right, full fine-tuning. You update every weight in the model, tens of thousands of examples, multi-GPU clusters, deeper adaptation, but risk of catastrophic forgetting. The model gets better at your domain, but worse at general tasks. Further right, continued pre-training. You take a foundation model and train it on billions of tokens of your domain text. This changes the model's fundamental understanding of your domain. Massive data, massive compute, massive cost. Far right, pre-training from scratch. Build a foundation model on your domain corpus. Bloomberg did this with Bloomberg GPT. This is a research scale effort requiring hundreds of GPUs for weeks or months and hundreds of millions of dollars. For today, we're focusing on the 3 that matter for enterprise practitioners: LoRA fine-tuning, full fine-tuning, and continued pre-training. Let's go deep on each. LoRA, low rank adaptation, is the single most important fine-tuning technique for enterprise teams. Let me explain why. A foundation model like Llama 3.170B has 70 billion parameters organized into weight matrices across its layers. Full fine-tuning updates all 70 billion. LoRA says, instead of updating the full weight matrix W, we decompose the update into 2 much smaller matrices, A and B, whose product approximates the full update. If W is a 4096 by 4096 matrix, that's about 16 million parameters per layer. With LoRA rank 16, matrices A and B together have only about 131,000 parameters per layer. That's less than 1% of the original. But it captures the most important directions of change for your specific task. The original model weights stay frozen. You only train the adapter. This means 1. Dramatically less GPU memory. You can LoRA tune a 70B model on a single A100 GPU. Full fine-tuning that same model requires 32 to 64 A100s. 2. No catastrophic forgetting. The original capabilities are preserved in the frozen weights. Your adapter adds domain specialization on top. 3. Composability. You can train multiple adapters for different tasks. One for legal, one for medical, one for finance, and swap them at inference time on the same base model. QLoRA adds quantization of the base model, compressing it from 16-bit to 4-bit precision, while training the adapter in full precision. This cuts memory requirements by another 4x. You can fine-tune a 70B model on a single consumer GPU with 24 GB of VRAM. In practice, for enterprise, you'd use an A10G or A100 on SageMaker. But the point is, the infrastructure barrier is dramatically lower. The quality of your fine-tuning data determines everything. Let me be blunt. Garbage in, garbage out. And fine-tuning amplifies this principle. Your training data should be formatted as prompt completion pairs in JSON-L format. For instruction tuning, which is the most common enterprise pattern, each example has a system prompt, a user message, and the ideal assistant response. Here's what good training data looks like. First, it's representative. If you want the model to handle customer support queries, your training data should cover the full distribution of query types, edge cases, and response patterns you expect in production. Second, it's high quality. Every example should be a gold standard response. Have domain experts review and curate the data. One bad example in a small training set can measurably degrade performance. Third, it's diverse. Don't overtrain on one pattern. If 80% of your examples are simple Q&A and 20% are complex multi-step reasoning, the model will be great at simple Q&A and mediocre at complex tasks. Minimum viable dataset. 500 to 1000 curated examples for LoRA, but I have seen the best results with 5000 to 50,000 examples that cover the full task distribution. Key hyperparameters you need to know. Rank, the dimensionality of your adapter matrices. Rank 8 to 32 covers most enterprise use cases. Higher rank captures more complex adaptations but needs more data and compute. Start with 16. Alpha, scaling factor, typically set to 2x the rank. Controls how much influence the adapter has over the base model. Target modules, which layers to apply LoRA to. For transformer models, applying to the attention layers, Q, K, V, and output projections gives the best results. Some teams also include the MLP layers for deeper adaptation. Learning rate. 1e-4 to 3e-4 is the standard range. Lower than full fine-tuning because you're updating fewer parameters. Epochs. 2 to 5 for most datasets. Watch for overfitting after epoch 3. If your validation loss starts climbing, stop. Full fine-tuning updates every parameter in the model. It produces the deepest adaptation but comes with significant trade-offs. When you have enough data, 10,000 plus high-quality examples minimum, and you need the model to fundamentally change how it processes your domain. Not just what it says, but how it reasons. Examples. Training a model to follow a completely new output schema consistently. Adapting a model to reason in a domain-specific way, like legal syllogistic reasoning or clinical differential diagnosis. Or when LoRA experiments show the model plateauing below your quality threshold. This is where it gets expensive. A 7B parameter model like Llama 3.18b needs 4 to 8 A100 GPUs for full fine-tuning. That's about $15 to $30 per hour on SageMaker. A 70B model needs 32 to 64 A100s with model parallelism. That's $500 plus per hour. A typical training run of 3 to 5 epochs on 50,000 examples might take 8 to 24 hours. You're looking at $4,000 to $12,000 per run, and you'll need multiple runs for hyperparameter tuning. Here's the critical risk. As you train the model on your domain data, it starts forgetting its general capabilities. The model gets really good at your specific task, but starts performing worse on everything else. Mitigation strategies. Mix your domain data with general instruction following data. Typically, 20 to 30% general data in the training mix. Use a lower learning rate. Evaluate on both domain-specific and general benchmarks after every checkpoint. This is actually one of the strongest arguments for LoRA over full fine-tuning for most enterprise use cases. LoRa's frozen base weights naturally prevent catastrophic forgetting. Continued pre-training is a different beast entirely. You're not teaching the model a task. You're teaching it a language. The language of your domain. When a general-purpose LLM encounters the patient presented with a type 2 STEMI with LAD occlusion, troponin trending at 4.2, and an EF of 30%. It can pass the words, but a model that's been continuously pre-trained on millions of clinical notes understands the urgency, the relationships between these findings, and the standard of care. Continued pre-training doesn't teach the model to follow instructions or answer questions in a specific way. That's fine-tuning. It teaches the model to natively understand your domain's concepts, terminology, abbreviations, reasoning patterns, and implicit knowledge. Step 1. Assemble your corpus. You need a massive amount of domain text. We are talking millions to billions of tokens. Internal documentation, published literature, communications, reports, code bases, whatever represents your domain's language. Step 2. Clean and deduplicate. Data quality matters even more at scale. Remove duplicate content, boilerplate, low quality text. This is a significant data engineering effort. Step 3. Training. This is standard next token prediction, the same objective used to train the original model. The model learns to predict the next word in your domain text, which forces it to internalize the patterns of your domain. Step 4. Instruction tuning. After CPT, the model understands your domain but has forgotten how to be a helpful assistant. You need to re-instruction tune it, typically with a few thousand domain-specific instruction-following examples. This is often done with LoRA. Let's talk real numbers. SageMaker HyperPod with a cluster of 16 P548 XLarge instances, that's 128 H100 GPUs, runs about $800 per hour. A continued pre-training run on 10 billion tokens might take 3 to 7 days. That's $57,000 to $134,000 in compute alone, before data preparation, evaluation, and iteration. Bloomberg reportedly spent over $2 million in compute to train Bloomberg GPT. And that was a relatively modest 50B parameter model by today's standards. Bloomberg GPT, trained from scratch on 363 billion tokens of financial data. The model outperformed GPT-3 on financial NLP tasks by significant margins while remaining competitive on general benchmarks. Met Palm 2. Google took Palm 2 and instruction tuned it extensively on medical data with expert feedback. Achieved expert level performance on medical licensing exams. StarCoder, pre-trained on 1 trillion tokens from GitHub, dramatically outperforms general models on code generation across all programming languages. Be honest with yourself. Continued pre-training makes sense when your domain language is fundamentally different from general English. Heavily abbreviated clinical notes, legal statutes with specific phrasing, financial regulatory language. You have 10 billion plus tokens of domain-specific text. Not 10 million, 10 billion. That's roughly 7.5 million pages of text. RAG plus fine-tuning experiments have demonstrably plateaued below your quality requirements. You've tried the cheaper approaches and measured the gap. You have the ML engineering team and budget to support a months-long effort with multiple training runs. For 95+% of enterprise use cases, the answer is don't do this. The combination of a strong foundation model, RAG, LoRA fine-tuning, and good prompt engineering will get you further, faster, and cheaper. Let's get practical. 3 paths to fine-tuning on AWS. From simplest to most flexible. The managed path. Upload your JSON-L training data to S3. Select your base model, Titan, Llama, Cohere. Choose fine-tuning type. Bedrock supports both full fine-tuning and continued pre-training for supported models. Configure hyperparameters. Click Train. Bedrock manages the infrastructure, distributes the training, and gives you a custom model endpoint accessible through the same Bedrock API. You can use provision throughput to guarantee capacity. Limitations. You're limited to Bedrock's supported models and fine-tuning configurations. If you need LoRA specifically, or a model not on Bedrock, or custom training scripts, move to path 2. Full control with managed infrastructure. Use Hugging Face deep learning containers with your custom training scripts. SageMaker handles distributed training across multi-GPU instances, checkpointing, spot instance management, and model artifact storage. For LoRA fine-tuning, you'd use the PEFT library inside a SageMaker training job. For full fine-tuning, use DeepSpeed 0 or PyTorch FSDP for model parallelism. SageMaker distributes across your instance cluster automatically. After training, deploy to a SageMaker endpoint with auto-scaling or register in the SageMaker model registry for versioning and governance. For continued pre-training at scale, SageMaker Hyperpod gives you resilient training clusters with automatic fault recovery, critical for multi-day training runs where individual GPU failures are expected. Maximum flexibility. Spin up P5.48x large or P4D.24x large instances directly. Use training frameworks like Axolotl, TRL, or Llama Factory. Serve with VLLM or TGI. This path makes sense for teams with deep ML engineering expertise who want to use the latest techniques, custom training loops, or frameworks not yet supported by SageMaker containers. Regardless of how you train, you need to serve the model. Options. Bedrock Custom Model Import. Train anywhere, import into Bedrock, serve with Bedrock's managed inference. Simplest operational model. SageMaker endpoints. Real-time or async inference, auto-scaling, multi-model endpoints for serving multiple LoRA adapters on one base model. Self-hosted VLLM on EKS. Maximum performance tuning, continuous batching, speculative decoding, tensor parallelism. Best throughput per dollar for high volume workloads. Let me give you a concrete decision framework. Question 1. Does your use case require the model to generate domain-specific output consistently? Domain terminology, specific formatting, particular reasoning patterns. If yes, fine-tuning is on the table. If no, RAG and prompt engineering are sufficient. Question 2. Can you achieve the required quality with prompt engineering alone? Test with few short examples in the prompt. If the model reaches your quality bar with good prompting, don't fine-tune. You'll save significant time and money. Question 3. Do you have at least 500 high-quality, curated training examples? If no, invest in data collection first. Fine-tuning with bad data is worse than not fine-tuning at all. Question 4. Is the knowledge static or dynamic? If your domain knowledge changes frequently, new products, updated policies, changing regulations, fine-tuning will go stale. Use RAG for dynamic knowledge and fine-tune only for stable behavioral patterns. Decision. If you answered yes to 1, no to 2, yes to 3, and your knowledge is stable, fine-tune with LoRA. Start small, measure rigorously, scale up only when evaluation data justifies it. Key takeaways. LoRA is the enterprise default for fine-tuning. Low cost, low risk, composable adapters, no catastrophic forgetting. Full fine-tuning is for deep adaptation when LoRA plateaus and you have the data and budget. Continued pre-training is for specialized domains with billions of tokens and clear gaps that simpler approaches can't close. Always try prompt engineering and RAG first. Fine-tuning is an optimization, not a starting point. In part 3, we are covering prompt engineering and caching, the techniques that require zero infrastructure changes but can dramatically improve quality and cut costs. System prompts, few-shot learning, chain of thought, semantic caching, and memory management. These are the techniques you'll use in every single deployment alongside RAG and fine-tuning. See you there.